Good morning, students. So today we are going to discuss another important topic. So before going to say this uh, another topic, just we will try to recall what we have discussed in previous. So in previous class we have discussed what is a VLSI and what is the importance of FPGA. FPGA architecture we are discussed. Then FPGA architecture. And again two types we are discussed what are the advantages and applications. The first one is 4000 FPGA is the first generation FPGA, and later on second generation FPGA is the 8000. So 8000 FPGA also some of the advantages and applications we have discussed. So now today we are going to discuss the another important design in this FPGA is 10K FPGA. So what are the advantage of this 10K advantage 10K FPGA? So previously what is the difference between 4000 and 8000 is, so we are going to increase the memory, So here also by using this 10K we are going to increase the memory size of the not only the memory size, different applications also going to be increased. So what is the difference between 8000 and 10,000 is, so additionally we are going to have a one more block is called as EBA, and similarly we are going to have a interconnects. So what are those interconnects? It is a column interconnects are there, and as well as row interconnects. Additionally we are going to say this column interconnects and as well as row interconnects. As already we are saying this input output elements, we know this. So logic array elements we know, logic array blocks also we know. So now additionally we are going to incorporate EBA and column interconnects and row interconnects in this 10,000 K. So now we will see what are the advantage. So in this we are going to see this how many LABs are there. We have a 72 LABs. 72 to 1520 LABs. So this is the one of the advantage. So as already we know, in each LAB we know how many logic elements. We have a 8 logic elements, as already we are seeing in 8000. So if it is a 8 logic elements are there, then we are going to how many LEs are there? We have a 576, and similarly 12,160 LEs are there. So if it is this much of LEs are there, as we know how many gates are going to be used in the design. So in this we are going to 10,000 gates we are going to be used, that is the advantage, and similarly 2,50,000 gates we are going to be used. When compared with the 8,000 and 10,000, more number of gates are going to be increased. What is the meaning of increasing the more number of gates? So it indicates the size of the memory is going to be increased, and as well as number of applications are going to be increased. And one more important point in this is EBA. As already we have discussed, what is the advantage of 10K FPGA is EABs. So in what is the EAB? Embedded array block. So how many embedded array blocks are there? We are going to have 3 to 20 EABs are there. So in this 3 to 20 EABs, so we are going to have a RAM of number of bits we are going to have 6146 and 40,960 of RAM values are there. So we know what is the RAM, random access memory. So the random access memory, what are the data we are receiving and what are the data we are forwarding. So that is the sending and receiving operation is going to be depends on the RAM value, random access memory. So it is going to store the data and it is going to forwarding the data. Now, so if you see the circuit, in this we are going to have a LEs are there, LE1 to LE8 like this. The internal structure of this one, what is the internal structure of LABs? This is internal structure of the LAB. So we are going to have LE1 to LE8. Totally how many LEs are there? As already we have discussed. So 576 to 12,160 LEs are there. So these are all interconnect to this row and column interconnects. So this is the internal structure of LAB. So each LAB we are going to have a lookup table there, and similarly we have a carry chain. So all these are going to be connected one LE. So within a one LE, this is the total circuit as is going to be incorporated. So next one is a logic elements. How many logic elements are there? So these are the number of logic elements in a single LE. So in this we have a LUT is there, and we have a AND gate is there, and number of LUTs and number of AND gates we are going to have, and this is going to be the OR gates. So we are going to choose whether design has to be done based on the AND gate or design is going to be done on the OR gate. So here we are going to have a different flip flops we are going to use. We are going to use the D flip flop, T flip flop, and JK flip flops also. So this is also a one interconnect for this LEs. Next one is a Xilinx XC4000 series is another company is started designing the FPGA. So that company name is called as a Xilinx. In a Xilinx, their first design is XC4000 series. In XC4000 series, so what are there in the XC4000? So in this we are going, as already we are observed, LUTs are there and multiplexers we have, and we are going to use the registers and more is a control signals. These are the different blocks are going to be incorporated in XC4000. So it is a, what is the input delay is, the delay is only 5 nanoseconds. So delay is 5 nanoseconds. What is the meaning of 5 nanoseconds is very less time it is going to be taken to perform the operations. So this is the advantage of this design XC4000, and these are all are interconnected blocks we are going to have, and we have a previous designs are XC3000, XC4000. These are the similar family, and we are going to see the next one. Its a delay is only a 5 nanoseconds, very less delay. So in this we are going to have, this is a design of internal architecture of the, this is internal architecture. So in this internal architectures we are going to see input output blocks as already we have discussed previously, and CLBs also we know. So what is the additional advantage of this one is switch matrix. So in this design, switch matrix is plays a vital role. So what is the, due to this switch matrix, so the time delay is going to be reduced. That is the main observation in this XC4000, and we are going to have a vertical long lines and as well as horizontal long lines are connected. So previously vertical matrix we are observed, but here we have a vertical and horizontal long lines also we are going to have to interconnect all are interconnected with a switch matrix and CLBs, and CLB switch matrix also interconnected to input output blocks. And the next design is a Spartan. So Spartan XL is another important design. It is from, again it is from the company name is a Xilinx. So what is the advantage of this Spartan XL is, we are going to have a 40,000 system gates are going to be used. 40,000 gates are going to be used, and one more thing is we have a RAM selected memory, and we are going to have a another one is peripheral component interconnects. Peripheral component interconnects are going to be used or incorporated in the design of Spartan XLs. And one more advantage of this one is this is bus complaint and having 8 flexible global low skew buffers, and this is also one of the important consideration in Spartan XLs. So what is the advantage of this is a fast capture of the data. So this Spartan XL, by using very high speed data are going to be operated with this design. These are the advantages. So here we are going to see some comparisons. So comparisons we are going to 05 XL is a one design, 10 is another design, 20, 30 and 40. So these are the different designs or improvements in Spartan XLs. So if you see what are the comparison of this, if you see the system gates, how many gates are going to be used in the design is, so initially in 5XL, 2K to 5K they are used, 3K to 10K, 7K to 20, 10K to 30 and 13K to 40K they are going to used in 40XL. So logic cells if you see 238 and 466 and 950, 1368, 1862 is a another improvement. So number of logic gates is also one of the important consideration. Initially in 5 we have a 3000. So if in case if you take is a 40XL, we have a 20,000 are there. If you see the flip flops also, for every design flip flops also are going to be increased from 360 to 2016, and maximum available input output pins. So available pins, and initially it is a 77. If you see 40XL we are going to have a 224 input output pins are available. So these are the basic advantages and improvements in the design. So another so frequency, based on the frequency we are going to decide whether it is a speed or not. So here they are going to use 200 megahertz of input output switches. It is also one of the advantage, and 2 lakhs of gates they are going to use in a Spartan 2. That is a one more advantage. So if they use 2 lakhs of gates, automatically the more storage is going to be increased. And one more important point is operating voltage. So what is the operating voltage of this one is only 2.5 volts. So 2.5 volts is also a very less voltage. So based by using this we are going to operate more, and we are going to have a multiple input output standards are there, and one more is delay locked loops are there. So these are the advantages. And what is the one more advantage is, so design technology. So the design technology is a 0.22 micrometers, or another design is 0.18 micrometers. So due to this technology, the size is going to be reduced. That is one of the important advantage in this Spartan 2. And we are going to have a on-chip memory in this. We are going to have a on-chip memory, and we are going to save the data. So this is the main advantage of this Spartan 2 FPGA. And if you see the block diagram of this, how internally connected, this is a block diagram of all this. Additionally, we are going to have DLLs. This is the advantage of Spartan 2. Advantage is this: 16 into 1 RAM, 16 into 2 RAMs are going to be used, 16 into 1 and 16 into 2 RAMs, and 32 into 1 RAM is also going to be used. And in this we have a 3 registers are there in each IOB, and we are going to use the D type flip-flops. So these are the very sensitive latches. These are sensitive latches, and we are going to have input output pads are there also there. So these are the basic advantage of this Spartan 2. So this interconnection circuit in a logic cell, and we have a LOT, carry and control logic, and as we are discussed, we are going to have a D flip flops are going to be used. So another design is called as vertex. So Xilinx are produced more number of FPGAs. So as we are started with the XC4000 and Spartan 1, Spartan 2, and after that they are designed another important FPGA is vertex. So vertex FPGA, what is the advantage of this? It is going to be used for complex system levels. Advantage of this design is, so we may use it complex system levels, and it is work as a SOC. It is also work as a SOC. So we are going to embedded more memory. We can increase the memory of this one, and we will reduce the time. We need to reduce the times, and we have a subsystem interfacing also is the one of the advantage. So due to this subsystem interface, the speed of operations are going to be increased. So previously already we have discussed, it is a 200 megahertz. So now it is a, how many bits they are going to use to increase the memory size is 3.5 megabits are going to be used. So due to this, the memory size is going to be increased, and we are going to increase the density and as well as the performance. We are going to increase the density and performance. So in this family we are going to use this different protocols to perform the more operations on this circuit. So this is the diagram how it is interconnected in the circuits. Right. So far we have discussed different designs of FPGAs and different improvements in FPGA, and finally we are going to conclude. This is, we have a two methods we have to follow. One is the design process, how we will design. Design process we know from top to bottom, and verification is bottom to top. So now again we are trying to recollect each one. So first one is for while we are seeing the design, first we are going to see the system level. So in a system level, what is there? We are going to write the program. So for our in VLSI, we are going to use the VHDL code or Verilog code. So these Verilog code or VHDL code under comes onto the system level. So once if you write the program has to be translated. So how to translate this? This is a system level to a register transfer level, system level to a register transfer level. In a register transfer level in a previous class, so we are going to convert the program into a basic elements. Basic elements are called as gates and flip-flops. So how the gates and flip-flops are designed? By using a resistors and transistors. So the resistors and transistors are designed and it is going to be frame the net list, that is going to be done by using a register transfer levels. So from it is moved from register transfer level to gate levels. We are going to use the different gates, that AND gate, OR gate, NAND gate, NOR gates, all this. So from this gate level, we are going to convert the gate level into a transistor level. So how we design the gate? By using this transistors. So the transistors again is going to move to the layout level. So the transistors are going to be moved to the layout level. So finally it is a mask level. So in a mask level means as already we are studied how to prepare a mask, N-mask fabrication, P-mask fabrication. So these are the fabrication level. So finally how a chip will be designed is, it starts with the system level and end with the mask level. So in a this process is called as a design process, while second one is the verification process. Where to start the verification? The verification is starts from the mask level. So mask level should be a perfectly designed, otherwise what happens, the memory size is going to be increased, the area is going to be increased. If area increased, power consumption is also increases. These are the problems are going to be encountered. That's why we need to check it in the mask level, then it is moved to the layout level. So any problem occurs in the mask level, then we have to recheck with the layouts. So layout level is going to be verified with the transistor levels. Again it is going to be verified with the gate levels. Again gate levels are verified with the register transfer levels. Register transfer levels are verified with the system level. So system level means what we are discussed, it is a program, whether it is a VHDL program or Verilog program. So therefore design will be top to bottom and verification is bottom to top level verification we are going to done. So in this next we are going to see how the RTL synthesis flow is going to be happen. So as already we have discussed just now, so here HDL program we are writing, so that is going to be converted to a transferred to library. Library will prepare the netlist. So that netlist is going to be synthesized. So it is going to be verified. The verified will become a netlist. So in a netlist, what is going to happen? Say this. This is the multiplexer and the gates we are going to have. So from that we are going to verify the logic. So whether this multiplexer and as well as gate levels or operations are correct or not is going to be verified. Then it is going to be again translated to netlist. So from the netlist we are going to have a physical design. So physical design, what is there in a physical design? So finally it is moved to layouts. This layouts is called as a physical design. So to understanding purpose we are going to convert the transistors or elements in the form of layouts. So this is a simple RTL synthesis flow. and as previously discussed, the code is converted to RTL and it prepares the netlist. Then it is convert into a RTL is going to be converted into multiplexers and flip-flops. Then that will be converted into netlist. Then it is going for the physical design. In physical design, we are going to do in the form of netlist. So this is a simple RTL synthesis flow. So finally, we are going to see high level synthesis. What is a high level synthesis? It is going to verified by using a behavioral synthesis, how it is working. Example, as already we have discussed, for example, take AND gate. So it verifies the truth table. So if verifying the truth table is called as a behavioral synthesis. So from the behavioral synthesis to RTL design. RTL design is nothing but, as we have discussed, registers, all this. So from RTL design to logic synthesis, whether the designed RTL is correct or not is going to be decided by using logical synthesis. So logically, logical outputs we are going to verify. Whether logically it is okay, then previous design is okay. Otherwise, we are going to moving back. So once logical synthesis is verified, so finally we are going to go for the gate level netlist. So finally gates are going to be prepared. That gates are going to be dumped into a FPGA. So finally we are going to verify the node points. So by using the node points, we are going to test the node points. If node point values are correct, so our design is correct. If it is not correct, then we send back to the designer. Again he will change his program and rewrite the program. Then again we are going to recheck all this. After checking, if it is operation node points are correct, finally gate level nest is prepared and it will be sent to the chip manufacturing. So therefore this is the a simple understanding of FPGA technologies. So these are widely used in VLSI design. Thank you.